Okay. Hello, everyone. Today we're going to be comparing and contrasting two different differential equation models for bacterial growth, and we're going to look at E. coli and Treponema pallidum. And this project is by me, Sarah Majeed, and Vladislav Mikheev. So the models we got were obtained from an article called Random Coefficient Differential Equation Models for Bacterial Growth by Dan Stanescu and Benito M. Chen-Charpentier. The first model we're going to look at for the differential equations is by Thomas Malthus in 1798, while the second one is by Verhulst in 1838. The bacteria types, I already mentioned them, which are E. coli and Treponema pallidum, and we got these from The Growth of Bacterial Populations by Kenneth Toder. And our changed parameter is going to be the growth rate due to different generation times of the bacteria. So E. coli has a generation time of 17 minutes and Treponema pallidum has a generation time of 1980 minutes. The equations we used is one per each model. The first one is dy dt equals r times y of t, where r is the growth rate in inverse minutes, y is the population size of the bacteria, and our initial condition is 1 bacterium. Our second differential equation is dy dt equals r times 1 minus y over k times y, where r is still the growth rate in inverse minutes, y is the population size of bacteria, and the initial condition is 1 bacterium. K is the equilibrium value of the bacteria, and it is equal to 200, and it's basically, we're going to see that it's the max capacity that the population of the bacteria will reach. And just a side note, there is an inverse relation between growth rate and generation time, where the higher the growth rate, the lower the generation time. And we're going to see these in our plots right now. And here are the Simulink models for the first differential equation.
Yeah. Here's the results. First off, for our first differential equation, it's pretty simple. It has nothing special. It only contains the integration of y and the constant values. And here is our resulting graphs for our first differential equation. As Sarah said before, the generation times play a big role on a population growth. So on the left side, here's the first type of bacteria. It has the generation time 17 minutes, which gives us the sharp increase starting from 250. And we definitely can see that the left graph is the exponential. But when we look at the right graph, which is describing the second type of bacteria, here's the generation time is 9080, so the graph is pretty much linear, and the growth of bacteria is not that fast. And here is our Simulink block diagram for the second differential equation that we used. It's a bit more complicated because it contains the equilibrium value, and the differential equation itself, it's a little bit more complicated than the first one, but it's still not that hard. So here's the results for using the second differential equation. Also, on the left side is the first type of bacteria that we've been talking about. As we said before, it has these 17 minutes of generation time. And as you can see here clearly, that the max amount of bacteria is 200. As Sarah said before, it's the K value. So as long as it has 17 minutes generation time, you also can see the sharp increase starting from 150 up to 450. But when we talk about the second type of bacteria that has the generation time 9080, it's still the linear. And here's our
here's our references. I just wanted to make a side little note talking about the relation between generation time and the growth rate. As you can see from our Simulink models, in order to obtain the actual growth rate, you have to divide 0.301 by the generation time, and this can be seen in our references. We got it from the Department of Agriculture in the US. And that's it.
Thank you for listening.